So section 3.6 is going to talk about rational functions. Typically we denote this with r of x, r for ratio, and here's your ratio. Both of these p of x and q of x are polynomials. And the ratio of those two leads to a very important class of functions that we're going to study a little bit. So let's take a look at kind of a graph to begin with, because I want you to understand some of the features about rational polynomials, and then we're going to dive into where they occur and why they occur. So let's start out by looking at this graph. Now you'll notice that the graph is really just the part that's in red, but for the sake of learning, we put in a couple of these lines, these dotted lines, and these lines are asymptotes. Now you've got a horizontal asymptote, and that's right here. Now if you put in 2 for your horizontal asymptote, most likely WebAssign is going to mark it wrong. I guess it depends how it asks the problem. Typically, when I ask for the asymptote, you're going to have to put in y equals 2 as the horizontal asymptote. If you just give me 2, does that mean x equal 2, which is a vertical line, or y equal 2, which is a horizontal line, or is 2 is a part of a coordinate? So make sure you do y equals 2 is a horizontal asymptote. And just as we had a horizontal asymptote, we also had a vertical asymptote as well. Keep in mind that your vertical asymptote is going to have the equation of x equals something. That's what gives you a vertical line as opposed to a horizontal line. And it also happens to have the equation that x equals 2. That's going to be your vertical asymptote. Let's look at a couple other things while we're looking at this one. Nothing really too spectacular. We can look at the end behavior. So that end behavior is asking, well, what happens to y as x is approaching positive infinity? Where's the y value getting closer and closer to? It's going to get closer and closer to this horizontal line, which is 2. So the limit there, the end behavior is that y would approach 2. So as x approaches positive infinity, y approaches 2. How about testing yourself on this? As x approaches negative infinity, what does y approach? And let me flip back to the graph. As x approaches negative infinity, going out negative x-axis, what's the y value settling down at? 2. Excellent. So that would also be 2. So that's typical. Now I'll give you the answer in one of your homework problems. Sometimes, depending on the problem, your graph can cross the horizontal asymptote. I mean, it does happen. You're not going to see that with your vertical asymptotes, but it can cross the horizontal asymptote. So keep that in mind as you move on these things. Now, how do you find these things if you don't have a graph to look at? Well, it's a good question. So for your vertical asymptotes are going to occur where the denominator is 0. So you're going to take your rational function and solve for their denominator is 0. Well, you know what? There's one more thing we can do here with this graph. Let's look at the domain and range while we got this one. Now I'll help out. The domain includes everything except the graph never really gets to this vertical line. Never gets to x equal 2. So that would be your domain, is everything but 2. Now, if you're going to say that in inner rotation, so let's see. There. It's everything but 2. So it would be negative infinity to 2, parenthesis, union 2 to infinity. That would be your domain. Likewise, in the vertical direction, for your y coordinates, the graph gets to everything again except 2. So if you take a look back at the graph, yeah, it doesn't quite get the 2 in either direction. So the range is all these y values except y equal 2. So it's going to be the same as the domain, at least in terms of the intervals we'll use. So the range is going to be negative infinity to 2. So that's this part down here, negative infinity up to 2, and then 2 to positive infinity. Now be careful. On the last test, a lot of people, when I asked for domain and range, they would give me coordinates of this point to this point. They give me both x and y coordinates. Domain and range are just intervals, either along the x-axis or along the y-axis. And they should look like this, lowest to highest, lowest to highest. So if you write infinity to 2, yeah, I kind of know what you mean, but you might lose a point, all right? I do want you to get into that habit of writing it in the correct way. All right, let's go back to example B now. So R of x is x squared plus x divided by x plus 1 times 4x minus 12. And let's work on finding the asymptotes, the vertical asymptotes first. So the vertical asymptotes those are going to occur where the denominator is equal to 0. And if you look at your handout, I think I've said a lot of stuff about those types of things on your handout. So that's this one here, right here. Vertical asymptotes, you find it by setting the denominator equal to 0 and solving. We're not going to worry about imaginary or complex solutions. We're just looking for the real solutions. If there's an imaginary or complex, don't worry about it. It's not going to concern us as far as this type of problem is concerned. So I want to know where this is equal to 0. Vertical asymptotes, so it's going to be x plus 1 times 4x minus 12 equals 0. One of these we can read off. The other one we might almost be able to read off. The first one is at negative 1. The second one, all right, if you don't want to do this in your head, I don't blame you. But we're going to set each of these equal to 0 and solve. And this one solves when x is equal to 3. So those are your two vertical asymptotes. These are also points that you want to throw out of your domain. Your domain can't include those. So as kind of a side note, our domain, negative 1 and 3, would be negative infinity to negative 1, negative 1 to 3, and 3 to infinity. That would be your domain. You have to throw out those points. And I can maybe squeeze in a union here and here.
Do we include the domain with that, the asymptotes?
Well, these points are the asymptotes. Those are the equations of the asymptotes. And these are the points you have to throw out of the domain. So I'm not sure exactly.
I just mean, if the question is what are the vertical asymptotes, do we have to solve for the domain? Or
No. I just threw this in as kind of like a bonus.
Yeah.
No. As far as the vertical asymptotes are concerned, those two would be the equations you want to use. And please, again, give me an equation. Don't give me just negative 1 and 3. I get a little bit uneasy about that. Now, what about the horizontal asymptotes? For the horizontal asymptotes, there's really 3 cases. And it kind of depends on the equations here. If the degree of the numerator, that's your p, if the degree of the numerator is less than the degree of the denominator, then you get y equals 0. That's your horizontal asymptote. If the degree of the numerator equals the degree of the denominator, then this is the interesting case. Y equals a over b. The ratio of those leading coefficients, that's going to be your horizontal asymptote. So, and the last one is an oblique asymptote, but I don't think I really go into those too much. If you divide the numerator by the denominator, you'll get a quotient plus a remainder. Y equals the quotient, that's going to be your oblique or slant asymptote. So you see that, like here, I've already pre-drawn an example with a slant asymptote or oblique asymptote. Let's go back to here. I'm going to FOIL this out in the denominator. That's going to be x squared plus x in the numerator. In the denominator, I'll get 4x squared minus 12x plus 4x. So minus 12 plus 4 is minus 8x minus 12. And the key thing to see here is the leading coefficients. I guess the other key thing to see is that the degrees here match, right? They're the same. If they're the same, let's just put a 1 there for our convenience there. And I'll do this one in color as well. I'll put a 4 here. So a 1 and a 4. Now this works because these degrees match in the numerator and denominator. Your horizontal asymptote is simply going to be y equals 1 over 4. And that 1 and 4 come exactly from these coefficients here. That's it. That's the nice case. That's one of two nice cases. The oblique asymptote, the third case, is kind of a little bit more of a pain. But let's check some of this in a minute. There's probably a couple more things that I'd like from you. I want to know the x-intercepts. Now, how are you going to find the x-intercepts? Well, you find the x-intercepts when you set y equal to 0. So that means you'd have 0 equals p of x over q of x. But there's kind of a shortcut. If you're trying to find the x-intercepts, then it really just amounts to finding where the numerator is equal to 0. You don't have to worry about the denominator 0. You have to worry about where the numerator is 0. So let's do that. So we'll set the numerator equal to 0. That's going to be x squared plus x equals 0. That's going to be x times x plus 1. And I hope that you're good enough at this point you can just read off those two values, x equals 0 and x equals -1. The last thing to kind of follow this up with is the y-intercepts. Y-intercept. And if you're actually really sharp, you'll already see that we kind of got the y-intercept already. But in general, you're going to set x equal to 0. And if I set x equal to 0 all the way back up here, r of 0 is going to be 0 squared plus 0 over, I don't know, whatever. It's going to be 0 over something, which is going to be 0. And we kind of already saw that. We knew we had a 0 at 0. So basically this graph should pass through the origin at least once. And it should cross the x-axis someplace else at -1. It should have vertical asymptotes at -1 and 3. And a horizontal asymptote at 1/4. Let's type this in and see if it matches all this stuff. Did any of you use Desmos on the first exam? Yeah? Okay. I like to. Remember, you can use Desmos on the exam provided that you use Desmos test mode and that you started it when we start the exam and stay on it. So we'll call this r of x equals x squared. There we go. R of x equals x squared plus x. And now I'll just highlight all this and hit the divide key. Divided by, I'll do x plus 1 times 4x minus 12. If you're kind of lost, like, oh my gosh, this is kind of a weird graph, hit the home button. There you go. That's a little bit better. And, you know, maybe I can zoom in a little bit from here. Actually, I'm not seeing all that I want to see. I see my vertical asymptote at 3, but there's another vertical asymptote that I'm missing, right? What am I missing? Negative 1. Oh, wow. I know why this is not the example I really wanted. At negative 1, the graph is undefined, but oh boy, this isn't. I'm sorry. Q of x equals. Let's factor out that numerator, right? It's x times x plus 1 divided by x plus 1 times 4x minus 12. So that's the same graph, right? I just factored it. But other than x equal negative 1, these terms cancel, right? So yeah, essentially what we've got is, say, s of x equals x over 4x minus 12. That's our graph. It's just that it's undefined at negative 1. Boy, I will not trick you like that. This is stuff that you'll see in calculus, though, so it's not bad to see here. Now, what's going on here, and let's take a look at this one, is that this graph is not defined at negative 1, because you'd end up with 0 over 0. And let's check that out. If I'm good enough, right here at negative 1, come on, there you go, right there. See that? There's a hole in the graph. You're going to see those kinds of things in Calc 1. Where you have to deal with a hole in the graph. All right, it's not something we're going to have to worry about here. I totally missed that, my bad. But, you know, a good teachable moment. I'm not gonna bust your chops with it on the exam next week, though. But in general, this is still real good. You're still going to look at the horizontal asymptote. Horizontal asymptote is going to be 1 over 4. Let's see that. Let's see that happening. And you can see it if you were to actually graph y equals 1 over 4. And let's do that. Y equals 1 divided by 4. There's your horizontal asymptote. And it looks pretty good. You move out and the graph is getting closer and closer to that line either direction. So nice, nice. It has a y-intercept at 0. And let's see, what else did it have? It's undefined at negative 1, so we're okay there. But it's got our vertical asymptote. I can put that in as well. That's something you can't do on your graphing calculator. X equals 3. So it just kind of frames the graph a little bit, so it looks nice. All right, my apologies. That was a little bit different than I expected. I didn't quite notice that. It was subtle. Sorry about that. Let's look at this one. There's an example like this online here. So this is example C. Is there any vertical asymptote here?
Doesn't look like it. It might be the origin.
Yeah, but a vertical asymptote would be, it'd be going up and up and up forever, and down and down and down forever, or both, or you know, whatever. But this one's not doing that. This one's just kind of sagging here in the middle, and then going off to the side. So it has no vertical asymptote. How about a horizontal asymptote? Does this one have a horizontal asymptote? Yeah. Horizontal asymptote is y equals 2. Beautiful. Its domain would be negative infinity to infinity, at least the way the graph looks. So its domain would be negative infinity to infinity. How about the range, though? Range is the y value. So it actually gets down and touches -6. So you would include -6 with a bracket. So -6 like this, up to 2. But is 2 going to get a bracket or parenthesis? Well, the graph gets close to, but never quite touches 2. So we're not going to include 2 in the range. It would get a parenthesis. That bothering you? You okay with that?
Sorry.
No. Are you okay with our conclusion on the parenthesis here?
Oh, yeah.
Okay. All right. That's good.
Would it not be infinity, not 2?
Well,
6 to 2?
-6 to 2.
It can only go to 2.
This is kind of petering off. It's getting close to, but never quite touching 2. So it doesn't get above 2. It doesn't even touch 2. So we're not going to include 2 with the parenthesis there. Okay. Find all vertical and horizontal asymptotes. I'm really hoping. In fact, I know this one's not going to do anything to us like example 1 did. That was really a bummer. So example D, S of x equals 16x squared plus 1 over 4x squared plus 10x minus 14. Ugh. Now, I don't know about you, but I was never really good at factoring these kind of things. We have to figure out where the denominator is equal to 0. The denominator equals 0 is going to tell us what?
Vertical asymptote.
The vertical asymptotes. Good. So let's work on that part. So that means our vertical asymptotes is going to be where 4x squared plus 10x minus 14 equals 0. Personally, if I was stuck doing this without, lots of help, I would take advantage of the fact that you can divide out a 2 from everything, right? Just make your life a little bit easier. That's 2x squared plus 5x minus 7 equals 0. That's looking a little bit better. Now it's up to you. Maybe you're good at factoring these things. I was never good at factoring these things. At least not when I was sitting in your chair. So you can use a quadratic formula, or you can try and factor it. Is there another way we could try and make our life a little bit easier here? How about, I don't know, what's my go-to to make our life easier? Desmos. Yeah, let's use Desmos. All right. So I'm going to graph y equals 2x squared plus 5x minus 7. All right, and I'll shut this graph off here. And what I'm looking for is where this actually equals 0. All right, so that's going to equal 0 exactly where this graph crosses the x-axis. So let's see if I get lucky and got a couple nice easy points. Bam, I do. 1 and -3.5. So I've got x equal 1 and x equal -3.5, which I'll write as -7 over 2. Those should be my vertical asymptotes. I really don't have to go any farther than that. just as a reminder, kind of coming full circle with stuff we've done earlier, x minus 1 equals 0, 2x equals negative 7, or 2x plus 7 equals 0. What I just did was I just came up with the factorization of this polynomial. So, okay. All right. So 16x squared plus 1 over x minus 1 times 2x plus 7, and there's a 2 out in front. I don't need it factored, just threw it out there. So we got our vertical asymptotes. What about our horizontal asymptote?
Would be 4.
Yeah, we want to look at the ratio of a couple things. Notice that these are the same. So the horizontal asymptote is going to be the ratio of this one to this one. So it's going to be y equals 16 over 4. 4. Beautiful. Done. How about the y-intercept? How are we going to get that?
X is 0.
Set x equal to 0. Cool. So basically, s of 0 should give me my y-intercept. Let's put in a nice 0 this way. S of 0. In the numerator, it's going to be 16 times 0 squared. That's just going to be 0. I'll get 1. In the denominator, I'll get negative 114 or negative 14. Because I'm using this form of the denominator. Both of those terms would be 0 minus 14. So kind of a small y-intercept. That's okay. As far as our x-intercepts, I'd have to set the numerator equals 0. And that'd be 16x squared plus 1 equals 0. And hopefully you wouldn't go farther than this to realize what? If you had x squared equals negative 1/16, there's no real solution. Right? Because if you take the square root of both sides, you're going to get a complex number. You're going to get an imaginary number. So this graph should not cross the x-axis. Just shouldn't. So it should be on one side or the other. In fact, it'll probably cross, it'll change sides of the x-axis, I think, at these points. But it'll never actually touch the x-axis. Now, there's nothing wrong at all with actually looking at these graphs. So does everyone have this copied down? Can I switch to the graph? All right. Let's take a look at that. Let's see. It's going to be 16x squared plus 1 divided by, where was it? It was 4x squared plus 10x minus 14. Now I'm zooming in a lot here because I wanted you to see one thing. I think, Nick, you're picking up on it.
Yeah.
That it actually doesn't touch the x-axis. This number, if you type in negative 1 divided by 14, there you go. That number was our y-intercept. So it matches pretty good. It also matches what we expected in other directions or other ways. So we've got x equal 1. We've got a vertical asymptote here. x equal negative 3.5. Let's put that in. X equal negative 3.5. Yeah, that looks reasonable. And we had a y, or a horizontal asymptote, y equals 4. Whoops. Did I make a mistake here someplace? I must have. Oh, it's all right. So this is an example where the graph actually crosses the asymptote. I mentioned before that that can happen, and this is just one of those examples. But you can see that eventually the graph does settle down to y equals 4. Yeah, it does dip below it for a moment, but then it stays on that one side. It gets forever closer from the underside.
Oh, so it doesn't necessarily mean that it can.
Yeah, it can cross its horizontal asymptote. All right. Now, depending on the function, sometimes you'll see it bouncing up and down around the horizontal asymptote, but not in this class. Not in this class. You're not going to see that kind of function. That's going to require a trig function that we're not covering. So, looking good there.
So
Excellent.
And sorry, this is just kind of a technical question, but an asymptote isn't necessarily where the graph can't be. It's just like
It's where the graph is eventually going to get close to. So, like x equal negative 3.5, that's a vertical asymptote. Eventually, the graph's going to get close to that. It might not touch it. You know, with your horizontal asymptotes, you can touch a horizontal asymptote. You're not going to touch a vertical asymptote. So these will never actually touch. This graph in green will never touch the graph in black. But the graph in green can touch the red graph. It's just that usually, once it gets on one side of the graph, it'll probably stay there. Okay? Now let me see if I've got this one still. Transforms. Yeah, just going back here, just to let you know that people actually do use rational functions. A couple weeks ago when I modeled the coronavirus data here in Michigan, I actually used a rational function. Now, it's a pretty ugly one, but hey, I got a good fit. I got a really good fit with this data. So, kind of cool. You could actually find the horizontal asymptote if you want to take a look at the ratio of this number and this number. I'm not sure it's going to be anything really appealing, but you know, it is going to be the horizontal asymptote at some point. You probably have to go out a long, long ways to get there.
That's cool. Would that be like, is that a math project sometime to like look up something like this? And
Yeah, you could, you know, maybe model something. Rational functions, I mean, that's literally how a lot of your calculators do some of their work. When they find a value for you, when you hit the trig buttons or the log button or other things like that, a lot of times, now this is proprietary stuff, so I'm just kind of guessing, but a lot of times you're using rational functions. So, you know, they might be ugly ones. Rational functions were a big part of my master's thesis. So, good stuff. All right. Almost done here. Back here. Let's see. Maybe we can read off some of these things here. Let's see what we can read off. How about the vertical asymptotes for example G? Can we read those off? Have we done enough work here that we can just read these off? What would be the vertical asymptotes?
Oh, it's 6 and -1.
X equals 6, x equal -1. Perfect. Somebody at home, maybe throw in something in the chat. What would be the horizontal asymptote? And while you're thinking about that, I'm actually going to write this down. So this is example E here. S of x. Teen. Well, let me give you maybe a little bit of a hint in this regard. You know what? We haven't done one like this, so my bad. It wasn't necessarily a fair question. This would be x squared plus 1 minus 6. It would be minus 5x minus 6. But the thing to catch here is that the numerator degree is 1 and the denominator degree is 2. So the degree of the numerator is less than the degree of the denominator. That means eventually this graph is going to settle down to 0 as your horizontal, oops, wrong dot, right here. You're going to have y equals 0 is going to be the eventual horizontal asymptote there. So that's in the case where the degree of the numerator is less than the degree of the denominator. What else can we do? We can set x equal to 0, s of 0. 0 is going to kill that term, so I'm going to be left with negative 18 over negative 6 times 1, which is negative 6. So s of 0 should be 3. That's going to be your y-intercept. When you set x equal to 0, you're going to get the y-intercept. What about setting the numerator equals 0? Numerator equals 0 gives you the x-intercept. You don't have to worry about the denominator. 6x minus 18 equals 0. I'll just jump to the happy ending there. X equals 3. That's your x-intercept. So, nice. The domain would be everything except negative 1 and 6. The range would be everything except 0. You know, I'd have to look at the graph. I don't know. That's a good question. What would be the range on that one? Let's take a look at the graph. New graph. Come on, new graph. 6x minus 18 divided by x minus 6, x plus 1. Oh, how about that? So because of this little thing here, the domain is the range is actually everything. This goes up to positive infinity and goes down to negative infinity. If I didn't have this little middle piece here, the range wouldn't include 0 because you don't have a 0. It's approaching 0 from above, approaching 0 from below. It's not touching 0, but it does touch 0 right here. So the range is everything. That one's interesting. Cool. I think that you've got the highlights here from this section. Are we doing good on this? Are my homies still with me? All right, let's stop things and get you on your way. Good luck with this stuff.